Hey everyone, and welcome to the 6th 3D Buzz Math VTM. My name is Rob, known on 3dbuzz.com simply as Dimondo. And with me tonight we've got...
Logan Frank.
Excellent. So, in the previous few lessons, as you guys may recall, we were talking about geometry. A lot of triangles and lines and so on and so forth. In this lesson, we're going to continue on with the geometry discussion and talk about some polygons, mostly quadrilaterals, but some other information about polygons as well. However, before we start and talk about all of this, let's get some answers for the previous questions. So, if you recall, the first question was to get all the sides from the two triangles, or rather, all the sides and angles from the two triangles. So as you can see here are the solutions. If they are wrong, then please correct me on 3D Buzz. I did this pretty quick. And then for 2, 3, and 4, here are the solutions. Just pause your video here and make sure you got the right answers. The relationship for solution 3 of 5 is that the area relationship is the square of the side relationship. And also, the reason that you see two values... I'll grab the pen tool. Felt tip pen. You see 1.45 or 0.69 as the ratio is that it depends if you took the bigger or the smaller triangle as your numerator when doing the ratio. But they have the same value. If you invert the numbers, so 1 divided by 1.45, you'll get 0.69, and so on. And finally, here's the solution to example 5 of 5. The important thing to realize in this one was that you had 3 similar triangles. Okay, so now that you had all the solutions, let's move on to the new lesson. Polygons. A polygon is a closed figure with a fixed number of straight sides. What this means is that a circle, which has essentially arc to it, is not a polygon. Similarly, if you drew, let's say, an ice cream cone, assuming I drew straightly, and then you had a little dome top to it, the dome top makes it no longer a polygon.
Makes sense, because then you can't really define sides of that. You like Rob just said, you would have to define that using an arc.
Right, and here's a nice cloud type shape. That's also not a polygon. Now that I'm done doodling, let's move on. If a polygon has all angles of equal size, all sides of equal length, and all the sides are symmetrically placed around a common center, then the polygon is known as a regular polygon. So, from that, it's important to realize that if this was an equilateral triangle, then that would be a regular polygon. A square is a regular polygon. A pentagon, 5-sided figure, is a regular polygon if it's like this. If it was, say, something different, 1, 2, 3, 4, 5, is that 5?
Yep, that's 5.
Then that would not be a regular polygon. And similarly, a hexagon, like this, is a regular polygon.
One way you can think about it is, with a regular polygon, you could draw a circle through all the vertices of the polygon.
Exactly. All the sides would be equally far away from the center of the circle. So from this, you can see that the cross shape over here, the plus sign, is not a polygon. Because even if you drew a circle, and imagine I drew really nicely, and this is perfectly circular, and it's not, but imagine it was.
Yeah, we're missing all those inside vertices.
Yeah, all these inside ones
you
here.
You have to have a separate circle to
and
get those.
Here.
And then what if we started moving some of those lines around? Then, I mean, it's not a regular polygon. You couldn't draw a single circle through all the vertices. Exactly.
So it's still a polygon, just not a regular polygon.
That's right.
Polygon names. So as you can see, depending on the number of sides, then each regular polygon has a different name, which makes sense. Also, it should be noted that there's a bit of, I'll say, not a war, but an argument going on among mathematicians. Some argue that a digon, meaning a two-sided polygon, should exist, and it would just be a straight side like that, straight. Other mathematicians say because that wouldn't be a closed figure, that won't be a polygon. Just thought you guys would be aware. It's a little information for your culture, for enrichment. In any case, and also here's the sum of interior angles for each of these regular polygons. So you can look at that, you might go, okay, so how do I know the sum of interior angles for a polygon given the number of sides? Well, if it's a regular polygon, like this pentagon down here, you can divide it into triangles. So a pentagon can be broken down to 3 triangles. Now, Logan, do you remember how many, without cheating and looking at the top of the slide, do you remember how much the interior angles of a triangle sum up to?
Well, they would sum up to 180 degrees.
Exactly. And we showed you that in the previous lesson. In any case, so if you have 3 triangles, 1, 2, 3, and they're each 180 degrees, then it's 3 times 180 degrees, which totals 540 degrees. So it's number of sides, in this case 5, minus 2, 5 minus 2 is 3, times 180.
So basically you have 2 fewer triangles than you have sides in any given regular polygon.
Exactly. So now we'll move on to concave and convex polygons. A concave polygon has at least one internal angle that is greater than 180 degrees. And as a kind of quasi-explanation to a convex polygon, it is simply one that isn't concave. That keeps it very simple. So a concave polygon is the one in the bottom left. You'll see that the angle here that I just circled is greater than 180 degrees. Whereas this convex polygon on the bottom right does not have any angle that is greater than 180 degrees. So another way of looking at it is that if you're inside a concave polygon and there's a predator hunting you, there is at least one location where you can be. Say I'm here, me. And the predator, labeled P, can be here and outside of his field of vision.
Another way to visualize that would be that in the case of a convex polygon, if you were to draw a line that passes through the polygon, that line would enter and exit the polygon exactly once.
Like that.
And in the case, and basically it would, that line could only enter and exit at exactly one point. In the case of a concave polygon, it would be possible to draw a line that could enter and exit the polygon more than once.
Right. Like this line.
For example, if you were to draw the line right there, then you would be able to enter and exit the polygon twice.
That doesn't mean, however, that every line will enter and exit more than once. For instance, this line only enters and exits once.
Right, the difference is that you can't do the multiple enter and exit on the convex polygon.
Exactly. Quadrilaterals. A quadrilateral is a 4-sided polygon. We will be dealing solely with planar quadrilaterals. What this means is that they're all flat. You can draw each one on a piece of paper. They're 2-dimensional. A non-planar quadrilateral would be one that comes into the 3rd dimension. It has a vertex where it... imagine this hourglass, if it tilted outwards, out of the screen at this vertex down here. If it tilted on there, then it would no longer be planar.
Right, it's basically if one or more of the points... has to be represented in 3D space, basically doesn't lie on the plane, then it would be a non-planar polygon. If it's planar, then it's 2D, and all points reside on a 2D plane.
Right. There are many different types of quadrilaterals, among which we will be dealing only with a few. There's a with there. It's imaginary. With a few.
Now for a bonus grammar lesson.
Exactly. Okay, so for instance, we'll be dealing with trapezoids, this one here that I just circled, and parallelograms, the one right beside it, but not with the 2 other quadrilaterals that are on the bottom right. Also, it should be noted that some people argue that the hourglass shape, because it intersects with itself, should not be considered a polygon. I don't follow this belief. And as such, you guys will be learning it as a quadrilateral.
I would say it all comes down to how you are allowed to define it. If you define it based on order of lines or order of vertices, that's how I would say what would define whether or not that is an actual polygon.
Yeah.
But in our case, we are defining it as a polygon.
Exactly. Squares. A square is a 4-sided polygon where all 4 sides are of equal length and all 4 angles are 90 degrees. The sides form 2 pairs of parallel lines, because they're all at 90 degrees. So, you kind of keep rotating and you end up with parallel lines. And the diagonals of a square perpendicularly bisect each other. So you'll see that the diagonals in blue hit at 90 degrees, and they perpendicularly bisect each other. So they're all halfway when they intersect over here. The perimeter, meaning the amount of measurement to get completely around it.
The sum of the sides.
The sum of the sides, thank you, Logan, is equal to 4 times one side. Or you'll see how I label one side as S. Whereas the area is simply the side times side, so S squared. Rectangles. A rectangle has 2 pairs of parallel sides. Opposite sides are of equal length. So as you can see here, the sides are equal length and parallel. It also has 9-degree angles. The sides of a rectangle are at right angles, like I just said. And all squares are degenerate rectangles. All that means is that not only does it have meet all the requirements for a rectangle, but it also happens that the opposite sides are equal and the adjacent sides are equal. So it's a degenerate, a special case. So the perimeter, the sum of the sides of a rectangle, is 2 times the sum of each side. So meaning M is being the vertical side, this one, N being horizontal side, this one. And if you take that, add them, M plus N, and double it, you'll get the perimeter.
So the sum of the adjacent sides times 2 gives you the perimeter.
Exactly. And the area is simply M times N. Parallelogram. A parallelogram has 2 pairs of parallel sides. So as you can see here, these little arrows represent parallel sides. Opposite angles are also equal. So as you can see here, A equals C, angle A equals angle C, and angle B equals angle D. So it turns out that also opposite sides are equal, as I said. So AD, the side AD, equals the side BC, and the side AB equals the side CD, meaning the lengths of the sides. So the perimeter is quite simply 2 times the base, meaning a horizontal side, plus the diagonal. And the area is simply base times height, where height I labeled as H in this yellow line. So base times height. It's also possible that you can have a height, if you rotated the shape, so now CD would be the bottom, and AB would be the top, and then DC would be this side here, and AB would be this side here. So as if we just kind of rotated it. Then you could have a height like that, and it would be the same formula. Base, which would now be CD times height.
Okay, gotcha.
Rhombus. A rhombus has all 4 sides of equal length, kind of like a square, and opposite sides are parallel, again like a square. However, the angles are not necessarily 90 degrees. So the diagonals bisect each other perpendicularly, and the rhombus is sometimes called an equilateral parallelogram because all 4 sides have equal length.
Makes sense.
So essentially, it's as if you had a square. I'll draw a square up here, and then you had the stick figure guy here, applying pressure to the side. He's pushing on it, and then the square in the next frame of animation, he's pushing on it, and now the square suddenly becomes lopsided, like that.
So it's kind of like skewing a square.
Exactly. So the perimeter is 4 times the side, because they're all of equal length. The area is the side times the height. And it should be noted that A squared plus Z squared equals 4S squared. A squared and Z squared, A and Z being the diagonals. So if you square the diagonals and add them, you get the square of 4 times the side squared. And I'm going to show you that in Photoshop. So we had a rhombus, I believe. So rhombus-y shape. Something like that. Beautiful rhombus. And there's our diagonals. Well, you might notice, if this was drawn properly, that the diagonals are each bisected. So that means you have 4 small triangles inside the rhombus, if you can see them.
And each of those triangles would be congruent?
Yeah, they're all the same because they have the same... they're all right angles also. So they're all congruent right-angled triangles.
Very nice.
So doing that, you can go, hey look, here's one of them. I'm just unfolding it. And then here are 2 others. And here's the third. Imagine they're all equal size again. So now I have the same 4 triangles that are once inside the rhombus. And this is 2 times the side, 2s, because each of these is in a side, s, 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 s. So you have 2s for the total hypotenuse.
Yeah, the total hypotenuse of 2 triangles.
And then, so 2s, and I completely just lost my train of thought.
We were going over the last question you were talking about in a rhombus.
Right, thank you. Okay, so you'll note each of these sides is 1/2 of the diagonal. You'll see it's bisected. So this whole thing is the entire diagonal. And this whole thing is the entire diagonal. So I'm just going to jump back to PowerPoint for a sec to remember my notation. I called them A and Z. Excellent. So I'll call this one A and that one Z. Now, if you remember back to the Pythagorean theorem, A squared plus Z squared equals 2S squared, which equals 4S squared. And that's how we just showed.
Very nice.
The proof that I was giving. Also, it should be noted that the area of this big triangle is equal to the area of the rhombus, because all we did is unfold it.
And basically just took every triangle like it was a separate piece and reassembled them into the triangle.
Right.
The final one.
So the area of the rhombus, which is side times height, is also equal to A times Z divided by 2. So that's equal to A, that's an A, times Z, all over 2.
Very nice.
And that, whoa, didn't mean to scroll like that. That's a Z. Okay, so that's everything you have to know about rhombuses. Or rhombi, or some such. Trapezoids. A trapezoid has 1 pair of parallel sides. So you can see that B1 and B2 are parallel. So, this is a standard example of a trapezoid. Often you'll see them where S1 and S2 are equal, something like this. But that doesn't have to be the case. S1 does not have to equal S2. They can, but that's a special case. It's also possible that you'd have something like this. If the top and bottom are parallel, you could have something like that, where it's kind of like moving this side.
So B1
top.
and B2 not only don't have to be of equal lengths, they also don't have to be. They can be offset from each other, and it's still
right.
It still is a trapezoid.
You can have an obtuse angle in it, is what I'm trying to say.
I gotcha.
Okay, so keeping that in mind, here's what we know: the perimeter is simply that you add up the sides and the top and the bottom. Very simple. Nothing. You'll almost never find an occasion where you need to use the perimeter of a trapezoid. There's nothing special, overly special about it. There is something special about B3, however. B3 is equal to 1/2 of B1 plus B2. So, a nice way to see that is imagine if you had a little triangle there and a little triangle here. If you took this small triangle and rotated it upwards here, you could fit it in perfectly up there. Do the same thing on this side with the S2, and you'd get a triangle up there. I hope this is clear. If you did that, and now you have this piece is no longer here, this bottom triangle at S2, and the bottom triangle near S1 is no longer there, you now have a rectangle with side length base length B3 and height length of 1/2 of h.
Very nice. So that could aid in calculating, and then as you see there, that aids in calculating the area of the trapezoid.
Which is how come B3 is very important. 1/2.
Because B3 is used in the calculation of the area.
Right, that's the area. That's B3 in the area. And that's how you can see that B3 also works like that. So with all of that covered, and I hope that was clear to everyone. If not, watch the slides again. It's video. We can move on to some examples. So try to calculate the area of the following figure. I'll give you a tip. You can calculate it in one of two ways. One way is to break it down into smaller polygons, all of which we talked about in this lesson. Or the other way is to remember back to the triangle lesson. Ignore the 5 units side. You don't need this piece of information. And use triangle information to solve for it. But you'll get the same answer both ways. Example 2 is also kind of similar. Here is a picture frame. All the gray area is your picture frame. You'd have a picture in here. So say me as a stick figure saying something like, I don't know, something short. Hi.
Excellent visual aid there.
Exactly, because there's text in pictures. In still pictures, there's always text. So, there's me in a picture frame. Now, you want to calculate the area of only the picture frame, not the picture inside of it. So, using the information given.
It's like a word problem now. It's like, all right, now gather what information was useful and what was not. Let's see, the area of the stick figure's head time. So, yeah.
Exactly. So now that I confused all of you, try to sort through that and find out the important information, like Logan said. And now that I keep scrolling backwards by accident, we'll go forwards to the end of slideshow. And thanks a lot, guys.
Very nice. Once again, thank you, Rob, for presenting the course material. And thanks to everyone out there who followed along. Take care.